Okay, so last time we had ended off just going over some of the basics. So we were just discussing mole fraction and mass fraction. Even in your guys' chemistry classes, you guys have probably dealt with that. So I'm not going to spend too much time going over it. But just really the definition of mole fraction, and we never actually use it this way, but it's just the number of moles of species I divided by the total number of moles. And for ideal gases only, the volume fraction of species I and the mole fraction of species I are actually one and the same. But if you use a non-ideal equation of state, say if you're doing supercritical combustion, or you have mixtures of particles and liquids and droplets and things like that, that is no longer true. Mass fraction is just simply the mass of species I divided by the total mass. And we will be using that one quite a bit. And again, we never actually use it like this. But by definition, the sum of mass and mole fractions must be 1. And note, if you look in some of the explosives books and in the explosive literature, they don't use Y, they use lambda for their mass fraction. I'm going to adhere to traditional combustion nomenclature, so my mass fraction will be Y. And the reason that is that in traditional combustion, the thermal conductivity is given the symbol lambda. And I know it's traditional in engineering to use K for thermal conductivity, but Ks are used for a different variable. And so for combustion, thermal conductivity is often used as lambda. Okay, so then using the mole fractions and or the mass fractions, we can compute the mixture molecular weight of a mixture of different gases. And the mixture molecular weight is simply the sum of all the mole fractions multiplied by the molar weight of species I, or equivalently, if you know the mass fractions, it's just 1 divided by the sum of yi over mwi. And so I'm not going to punch in the numbers, but an example, if we are using our surrogate air, which is the air approximate that I talked about, the molecular weight of that air, you'll find it to be 28.85 kilograms per kmol. And for numbers, remember that for surrogate air, the mole fraction or the volume fraction of oxygen was 21%. And since for an ideal gas, the volume fraction and mole fraction are the same, that means that the mole fraction is 0.21 and of oxygen is 0.21, and the mole fraction of nitrogen is 79%. And then using the chemical formula, you can either calculate the molar mass of diatomic oxygen, or you can look it up online. And same thing for nitrogen. So you just take these numbers here and stuff them into the equation here, and you get the mean molecular weight of the mixture. Okay, and so that's pretty straightforward. Oftentimes, it's just a pain in the butt to go and calculate all the molecular weights of all the different species. And note, if you know mass fraction or mole fraction, and you want to compute mass fraction, mass and mole fraction are related by this expression here. So now that we know the mean molecular weight of air, or of the mixture of the oxygen and the nitrogen molecules, and we know the mole fractions, you could use this equation here to compute the mass fractions. Okay. So those are pretty common things, and we'll be using those all the time. The other thing that we need to discuss is mass density, which is something you guys have been using in thermodynamics and fluid mechanics and basically all of your classes, and also molar density, which is also known as concentration. So mass density in species, I should say species mass density, rho, is just the mass of the mixture divided by the volume, which is just the definition of density. And now, if you want to know just the density of, say, the oxygen molecules, that would be rho sub I. and that's called the species density. And the species density is just the total density of the mixture times the mass fraction of that component. Okay, and then by definition, you can show that the total density of the mixture is just the sum of all the species densities. Okay, and now for molar density, that's called concentration. In combustion books, you'll see two different notations for that. You'll see square brackets and then species I, that could be H2O. And so if you see H2O in square brackets, that means the concentration of say H2O. And a lot of other combustion books, they will basically use C subscript I for concentration. Those are equivalent. When it's practical, I prefer using the square bracket notation, but that's not always practical. It gets a bit cumbersome sometimes. But really what the molar density is it's just the number of moles of species I divided by the volume. So it's the exact same thing as mass density, but basically rather than using mass, you are using the number of moles. Okay, and you can convert from species density to concentration for species I just by taking the concentration and multiplying it by the molecular weight of species I. Okay, so pretty straightforward. Okay, so now we're going to discuss chemical equilibrium, and I just need to get some notation out of the way. So for chemical reactions, in general, a reaction can be written as the sum over all species of basically nu I prime of species I. So this M here means chemical species I, so that could be H2O, CO2, etc. And this nu I prime is the stoichiometric coefficient in front of that species. So if you look at this example down here, we have a chemical reaction, and that CO plus 1/2 O2 goes to CO2. So this basically this portion here is for the reactants, and so here we have basically have 1 mole of CO plus 1/2 moles of O2. So for Mi is equal to CO, the stoichiometric coefficient would be 1. And for O2, the stoichiometric coefficient of the reactants would be 1/2. And then in general, that goes to the products. And the stoichiometric coefficient for the products are given by the notation nu I double prime. And you'll see that, and you'll see that quite a bit. And so the prime and double prime in this context does not mean derivatives or fluxes or things like that that used in either heat transfer or your calculus classes. Okay, and in a lot of reactions, and when we do chemical equilibrium, we will be interested in knowing the total change in moles for the chemical reaction. And now notice that that conservation of mass demands that we have the same number of each element in the reactants and the products. So that is, if we have one carbon atom, if we have one carbon atom on the reactant side, we can only have one carbon atom on the product side. And that is a consequence of conservation of mass. I'm not going to prove that in this class. That was proven in the previous combustion class, but we can just take that as a fairly intuitive result that you guys have probably been using since high school. But however, because the mass is conserved, the moles moles though, however, can be created and destroyed. So in this reaction here, we are taking 1 mole of CO and a 1/2 mole of O2, and those are combining to produce a single mole of CO2. So as this reaction proceeds, we are actually destroying destroying moles. Okay, and so that's just something to be aware of. And so the change of moles between the reactants and the products, it can be positive or it can be negative. Okay, and so I just have a small table here, or for this chemical reaction here, I just keep track of the nu I prime and the nu I double prime, and the change of moles of all those species for basically this chemical reaction here. And if you sum up all the delta n's for all the species, you'll find that delta n is equal to -1/2, which is sort of what we argued. That is that basically we are destroying 1/2 mole as the reaction proceeds. Are there any questions with this? Okay, moving on. Okay, so now we're just going to consider a standard reaction between fuel and air. So just as an example, we have basically methane plus A moles of air, or plus A units of air, I should say, and that goes to products. So first of all, we have some questions that we need to address. First, what are the products? And how do we deal with air? And then and then basically what is this A if we're going to assume perfect oxidation? That means there's no leftover fuel and there's no leftover oxidizer. Basically, what is A for this perfect oxidation? So for air, I'll go over that real quick. When you're dealing with the chemical reaction like this, it is more natural to work with basically work with 1 mole of oxygen. So if we use that, so basically we can then find to make to satisfy the empirical evidence that the mole fraction of oxygen in air is 29%, and we want 1 mole of air, you can basically go through and find how many number of moles of nitrogen you need, and you find that that is 3.76. And again, this is proven in a lot more detail in a traditional combustion class. Here we're just using the result. So this air here, if you're using this surrogate air, you can just say that air is equal to 1 mole of oxygen plus 3.76 moles of basically N2. And
Professor,
yep.
That is that's 0.2102 and 0.79 N2, right? Are those 21% oxygen and 79% nitrogen?
Did I get that wrong? I could have had a typo there. I'll look into that.
That's what we had on one of the earlier slides, I believe.
79 and 21. Yep, I think you're right. I'll fix that. But I will double check and make sure which one is sort of correct. Okay. Now, there's a very important thing, and it's a very common mistake even for grad students and even professors. I sometimes make it myself. In the above reaction, if you're going to treat air like this, the mass of the air is not equal to A times the molecular weight of the air. And the reason being is this does not account for the additional 3.76 moles of N2. So instead, for air, the mass of air would be the total number of moles in the air times the mean molecular weight of the air. Okay, and so MW air is just the molecular weight of this. And so there are 4.76. So for every mole of oxygen, you are carrying an additional 3.76 moles of N2. And so basically for every unit of air, there is not 1 mole of gas, there's 4.76 moles. So if you want to find the mass of air and you're treating air as this, you basically need to multiply it by 4.76 to account for these extra nitrogen molecules. Okay, so that's an important point. It's a very easy mistake to make, and I sometimes make it myself, in addition to typos in slides. So are there any questions with that? Okay, moving on. So now we need to learn how, so we've learned how to deal with air. Now we need to define, for if we want perfect oxidation, we need to define a concept called complete combustion. And really what complete combustion means is that the fuel and oxidizing elements in the reactants basically react to form their stable oxide. And so for the fuel atom CO, or the fuel atom C, the stable oxide for complete combustion is CO2. If your oxidizing molecule is oxygen, and if your fuel atom is hydrogen, your stable oxide is basically water vapor. Now, in traditional combustion, we only dealt with this portion of the table. But when we're dealing with energetic materials, we can deal with some rather exotic fuels such as aluminum or tungsten. Tungsten does burn. It's used sometimes in rocket nozzles, and tungsten, and then actually tungsten, even though it is a refractory material, it does burn. And basically what will happen if you use it as a rocket nozzle is the rocket nozzle will erode and get bigger and bigger and bigger. And so tungsten burns, magnesium burns, very energetic. Boron, it's sort of, in terms of particles, when we go over that in more detail, a very energetic particle, very difficult to ignite. Research in burning boron comes and goes. About every 10 years, there's a resurgence of basically boron particle combustion studies, and they almost always conclude the same thing, that it's awesome when it burns, but it's really hard to get it to burn. And now you can, now these energetic materials, the oxidizing element is also sometimes chlorine and also sometimes fluorine. And so now this table, which in a traditional combustion class where we only consider hydrocarbons, we basically only needed this portion of the table. With energetic materials, the size of the table explodes. And this is only a small portion of the fuels. There's basically almost every element you could consider. Titanium, all sorts of stuff, silicon, there's all sorts of fuels. So now we need to consider these stable oxides with these additional fuel and additional oxidizer elements. So if you're going to burn carbon with chlorine, the stable oxide is actually carbon tetrachloride. And if you're burning it with, say, fluorine, then the stable oxide is carbon tetrafluoride. If you're burning hydrogen with chlorine, the stable oxide is HCl. That's a gas. And some of you may be thinking, well, but that's an acid. When it's in gaseous form, it's not an acid. But if it becomes aqueous, or if it gets into innocuous solution, it becomes an acid, which is why it's extremely hazardous. Basically, if you are exposed to HCl gas, any HCl gas that touches your skin will become aqueous and turn into hydrochloric acid. Any HCl gas that you breathe in will become aqueous inside your body and turn into high molality hydrochloric acid. Basically, you get eaten from simultaneously from the inside out and the outside in, nasty stuff. And with basically fluorine, the stable oxide of hydrogen is actually hydrogen fluoride, and that's also very toxic gas. One way that you can make hydrogen fluoride in your house is if you are preheating a Teflon pan and it gets too hot and you see some smoke coming off the pan and you haven't put in any oil or butter or anything like that. A component of that smoke are the decomposition products of Teflon, and some of that stuff is and then some of that stuff is hydrogen fluoride. And if you breathe that in, you actually will get sick. As I found out when I was a grad student learning how to cook. So be careful with that. And then with and I'm not going to go through this entire table, but for aluminum, the stable oxide, when it reacts with oxygen is Al2O3. And the stable chloride would be aluminum trichloride and aluminum trifluoride, and so on and so forth. Now, when you start burning with these metals, the stable oxides are solids, and there are multiple crystalline structures that you need to consider. And so basically, if you want to find the stable oxide for these, you need to do some homework and find what is the stable oxide, because there's AlO2 and there's all sorts of there are all sorts of oxides of metal oxidation. But I just listed the most common ones that occur in combustion applications. But if you're considering something else like a slow oxidation, then the stable oxide might be it might be something else. Okay, and so that's just something to be aware of. Okay, and then and also in terms of oxidizing potential, fluorine is by far the strongest oxidizer. Basically, and chlorine is second, and oxygen is third. Okay. So yeah, a fluorine is so darn reactive. It will if you mix fluorine with, say, a stable metal oxide, Al2O3, which is actually just a different crystalline structure of sapphire. The fluorine is so reactive, it will actually rip off the oxygen molecules from the aluminum and actually form aluminum trifluoride. So it's extremely reactive, which is why it's useful as a compound in energetic materials.
Professor, can I ask a question?
Yeah.
So the terminology for you're saying oxidation for materials that aren't oxygen. Do we just use, is that, I guess I'm confused why we use that terminology, or how do we use that?
That goes to the really basic chemistry, the basic chemistry definition of it, where it has to do with the I can't remember that myself, but it's still called oxidation, even though it doesn't involve oxygen. It has to do with the transfer of ions and cations and things like that.
Okay.
Okay. Yeah, if you remember back to chemistry, like all those redox reactions and things like that, it sort of stems along those lines. Okay. Then you're making me dredge up chemistry that I haven't even thought about in many years.
Well, unfortunately, my chemistry is weak. I don't have a lot of training in that, so I may ask some naive questions.
That's all right. That's all right. Okay, so basically, yeah, the key point here is that the fuels in energetic materials can burn with all sorts of different oxidizers, usually usually these three, and you can also use all sorts of exotic fuels. And so you just need to consider what the stable oxide is. Okay. So now that we know what the stable oxide is for a variety of fuels and oxidizers, let's go back to our methane, CH4, plus this A, and I'm going to call that AST, and the subscript ST will be defined shortly. And we defined air as 1 mole of oxygen plus 3.76 moles of nitrogen, and that's going to go to products. And so we're going to first define a stoichiometric mixture, and that's the perfect amount of oxidizer supplied such that there's not any excess fuel or oxidizer in the products. So if we're going to define this to be a stoichiometric mixture, I will typically use the subscript ST. So AST means the stoichiometric basically number of moles of oxygen needed to perfectly burn all the carbon atoms and all the hydrogen atoms. So, so if we want to find the products, assuming a stoichiometric mixture, the only oxidizer here is the oxygen molecule. So if it burns completely, we can go back to that table and find that when carbon reacts with oxygen, the stable oxide is CO2, and with hydrogen reacts with oxygen, the stable oxide is H2O. So that basically means that basically means that all carbon atoms on the reactant side will basically go to CO2, and all hydrogen atoms will go to H2O. So if we apply that rule, we have one carbon atom. That means, and the number of carbon atoms have to be the same. That means we produce 1 mole of CO2. We have four hydrogen atoms. That means we produce 2 moles of H2O. So now we have the number of moles on the product side of CO2 and H2O defined. Now we need to find the amount of A, or the amount of air that is needed to basically balance that out. And so you can find, you can just balance the oxygen atoms on both sides, and you can find that the stoichiometric coefficient for air in this case is 2. So the final reaction, applying those rules, is basically CH4 plus 2 O2 plus 3.76 N2, and that goes to 1 mole of CO2 plus 2 moles of H2O plus 7.52 moles of nitrogen. Basically, nitrogen is almost treated, it's almost inert, but not quite. So for combustion purposes, we more or less treat it as inert, even though it does oxidize under very high temperatures to produce pollutants, but the time scales for that oxidation is extremely slow, unless you're dealing with shock physics and you're at like 15,000 Kelvin. But other than that, you don't need to consider it in terms of the overall reaction.
Hey, Professor.
Yeah.
In the second chemical reaction line
This
you have, yeah, why do you have 7.52 N2? Should that be like 3.76 times AST?
Yes, you are correct. I got ahead of myself.
Okay. So I was wondering how you do that already.
Yeah, I do that because I knew the answer.
Okay.
Sorry about that. And I'll post the updated slides. Okay. So now we know this. We know the stoichiometric reaction. Now we can find the stoichiometric air-fuel ratio, and that's normally defined that if this overall reaction is normalized such that you have 1 mole of fuel. So basically the stoichiometric coefficient of the fuel, which in this case is methane, is 1. Okay. And basically the stoichiometric air-fuel ratio is just defined as the mass of the air divided by the mass of the fuel at stoichiometric conditions. And so we can find the mass of the air. That would just be 4.76 times AST times the molecular weight of air, divided by the number of moles of fuel, which is just simply 1, times the molecular weight of the fuel. And so if you want to find the stoichiometric air-fuel ratio, you can use this equation here for a hydrocarbon. If you're using aluminum or something like that, or you're burning with a different oxidizer, then you need to basically adjust this formula for the things. So example for octane, you can find that the stoichiometric air-fuel ratio is 15.02. I will let you guys work through that yourself, and I have some intermediate answers for like the stoichiometric balance reaction and things like that. Okay, so are there any questions with that? Okay, so we will move on. Now in combustion, you will very commonly see a very important parameter. It's used way more often than the air-fuel ratio, but the air-fuel ratio is something that's used in a lot in like car engines and things like that. So, but the equivalence ratio is first, you consider the actual reaction, which may or may not be at stoichiometric conditions. So we can just consider 1 mole of fuel plus A units of air, and that goes, and that goes to products, whatever those products are for those particular conditions. And if the stoichiometric reaction and the actual reaction are normalized such that there's 1 mole of fuel, the equivalence ratio is really defined just to be the stoichiometric air-fuel ratio divided by the actual air fuel ratio. Okay. And so basically the numerator is the air fuel ratio computed using AST, and the actual air fuel ratio is the air fuel ratio not using AST but using the actual A that is used in the reaction. And you can go through some basic simplification and find that the equivalence ratio is just AST divided by A. Okay, and this is a very important parameter. You'll see it used a lot. And so if phi, or the equivalence ratio, is less than 1, that means you are fuel lean, meaning that you're going to have excess oxidizer, or it is oxidizer rich. Those are used interchangeably. If phi is 1, you're at stoichiometric conditions. And if phi is greater than 1, that means it's fuel rich, which means you're going to have excess fuel. You're going to have excess fuel in the products. Okay, and so for pollutant purposes, you normally want it to be as close to stoichiometric as possible, with certain caveats. Okay, so now we know how to find the products. We know how to estimate the products if we are at stoichiometric conditions. What if we're fuel lean? Well, if we're fuel lean, that means there is more than enough oxidizer to react with all of the fuel, with all of the fuel atoms, and any leftover oxygen is simply moved over to the products. So, for example, we take our methane, and basically rather than having 2 units of air, we have 3 units of air, and so now, when we find the products, you'll find that basically we will have 1 extra mole of basically oxygen, and that just moves directly to the right-hand side. Okay, and it doesn't really do anything. And now this is just, and so that's fairly straightforward. And this is really just a simplistic, like for back of the envelope type calculations. We'll go over this later, but to actually truly estimate what the products are, you need to do what's called a chemical equilibrium analysis, and that's usually using some sort of software package to basically do that. Okay. Now, so if the products are fuel lean, it's pretty straightforward. Just any excess oxygen just basically moves over to the product side. If you're fuel rich, that's way more difficult. There are only really rules of thumb. In this case, if you need accurate answers, I would really recommend doing a full chemical equilibrium analysis. Again, we will cover that later. But there is a nice rule of thumb if you just need a back of the envelope type like answer. And this is actually the result of a project I give in the other combustion class. And so what the result of that is that the students did a full detailed chemical equilibrium analysis of a hydrocarbon, and they basically went from an equivalence ratio of basically nearly 0 to up to, I think it was up to like 10 or something like that. And then they plotted the mole fraction of carbon, CO, H2O, and CO2. So you can see this. You can see all these different species. Their equilibrium mole fractions peak at different equivalence ratios. So if we start with extremely fuel rich, that is, we have almost no oxidizer available to basically burn them all, to basically burn the fuel elements, you can see that we produce a lot of carbon and soot. Okay, but as we keep adding more and more oxidizer, you notice that the CO goes up. So that means that all these carbon atoms are first reacting with oxygen to form CO. Then, if we keep moving to the left and we keep adding more oxygen, you find it's surprising, but we don't start producing CO2. Instead, we first start producing H2O. So then, if we keep adding more oxygen, the amount of H2O goes up, and that starts to peak. And then after that peak, if we add more oxygen, we start to produce CO2. And what's producing that CO2 is the burning of the carbon, or it's the reaction of carbon monoxide with the oxygen. Okay, and so this sort of result allows us to make a nice sort of rule of thumb, is that basically first, if you want to estimate the products, again, back to the envelope type calculation, you first take all of the carbon atoms and basically react them with the oxygen molecules to form CO. Then, if there are any remaining oxygen atoms, you take those oxygen atoms and have them react with H2 to form H2O. Then, after that step, if there are any remaining oxygen atoms, those react with CO to form CO2. So, for example, we can apply these rules for our methane, but instead of but we now only have 1 unit of air, like rather than 2. So there's clearly not enough oxidizer to burn all the carbon and the hydrogen atoms. So we first go to step 1. We basically look at the number of carbons, and we see that there are enough oxygen molecules to oxidize all of the carbon atoms to CO. So we're going to produce 1 CO, and that consumed one oxygen atom. Okay, so there's 1 oxygen atom left, and then that oxygen atom is going to react with the hydrogen to form 1 mole of H2O. Okay, and after we form that 1 mole of H2O, there are now no oxygen atoms left, and any remaining hydrogen just basically goes into the products as hydrogen. Okay, and so here it's a bit more complicated, as you need to apply this procedure, and any leftover hydrogen basically forms into H2, and basically any leftover carbon atoms goes to the products as carbon. Okay, so are there any questions with that?
It's interesting that the H2O doesn't also peak at the stoichiometric at phi equals to 1. Is that because of the efficiency, that it's not perfectly efficient? You're still getting
that. And one thing you'll find is that you'd think of, when we do equilibrium, you'll find that the peak temperature won't be at stoichiometric. It'll be just slightly fuel rich. And that has to do with some really sort of detailed chemical equilibrium stuff. And I'll probably talk about that a little bit because that is a fairly important result. I'll talk about that a bit when we discuss chemical equilibrium. Yeah, intuitively it's kind of backwards because people always think of, well, hydrogen is really reactive. So basically you would think that the first molecule, that you would preferentially make H2O before you made CO, but it's the other way around, which is really sort of surprising to me, but it is what it is. Okay. Any other questions? Okay, so now we've discussed this for fuels, are basically normal hydrocarbons. Now we need to extend this to energetic materials, all this chemistry stuff. And so here what we'll discuss is we'll define what an energetic material is. And I'm going to define a property called oxygen balance, because equivalence ratio and air fuel ratio don't really make sense when you are burning molecules by themselves. Where you're not introducing any additional oxidizer. Okay, and then we will discuss oxidation rules, and these are called the Kistokowski-Wilson rules. Okay, and so in combustion, and even later in this class, we dealt with the oxidation of fuels and oxidizers as separate molecules. So to react, fuel molecules must collide with, they actually must physically collide with oxidizer molecules. So for an example here, we have a CH4 molecule, and we have an oxygen, and we have an oxygen molecule, and they are going to collide. At the molecular level, they are going to collide. And so what happens is in this case is the O2 molecule crashes into this one H atom here, and it basically knocks it off, and combines with that H atom to form HO2, and then the fragment of the CH4 would be CH3. And that's really all a chemical reaction is for a hydrocarbon, is just a big giant game of billiards, and all the different products and chemical gases that are formed, our species, are just the fragments of all those colliding molecules. If the molecules collide with enough energy to actually fragment. Okay, and now in combustion, we showed that how fast this chemical reaction proceeds is proportional to the total rate of the collisions. Okay, so again, and that makes intuitively sense that for the reaction to proceed, there must be some sort of collision. And so, again, we will go over this in a bit more detail later on. But we showed from a kinetic theory type of argument that the reaction rate is really just based on the total collision rate times this Arrhenius term here. And just recall that the Arrhenius term is the fraction of successful collisions to promote chemical reaction. So you could imagine that if this O2 molecule is moving really slow and it just sort of lazily bumps into this H atom, it's not going to be enough energy to basically tear off this H atom, and it's just going to lazily sort of just push it out of the way. But if this O2 molecule goes flying really fast, and there's a lot of kinetic energy, it will actually then there's enough energy to basically rip off this H atom and then promote the reaction. Okay, and so but for hydrocarbons and gases, all a chemical reaction is really it's a giant game of billiards with all sorts of crazy fragments. Okay, now an energetic material on the other hand is different. An energetic material is a compound where the fuel and oxidizer are present in the same molecule. And so you could consider these as being pre-mixed, are mixed at the fuel and oxidizer are mixed at the molecular level, and they burn by themselves without any additional oxidizer or fuel. And they are often energetic materials are often made of a recognizable molecule such as benzene rings, and replacing some of the atoms with oxidizing or like energetic subgroups. And some of those subgroups include nitro, NO2. Is basically they'll take some of the hydrogen atoms and cleave those off, and the chemical engineers will then replace those with basically all these oxidizing things. And there's a whole slew of these things, and I have a table of them in the next slide. Okay, but the nitro group is very common. The nitrate group is common, and the perchlorate group is a very strong oxidizer. And I have a whole table of these. I'm not going to go through the whole table. I basically ripped this off from Explosives Engineering, and there's all sorts of things. There are nitrate groups that you can look for. Basically, nitroso, aldehydes, kete are basically ketone, all sorts of things. And so these are oxidizer groups. And for fuel subgroups, you can take H and replace it with a methyl group, or replace it with amino. And then there are all sorts of things that are added to these. So, and I'll just start listing a few of the common energetic materials. One you'll be doing a computer project on with a burning propellant would be RDX. I'm not going to even attempt to say the true chemical name for this. I'm terrible at pronouncing these things, but RDX, which is C3H6N6O6, it's a common ingredient in propellants. And physically, it is a crystalline substance. If you look at RDX powder, it doesn't look unlike sugar. And so really what RDX here is, you can almost think of it as they took a benzene ring, replaced 3 of the carbon atoms with basically nitrogen, and to those nitrogen atoms they attached a nitro group. Okay, and so basically here you can see in this one molecule they have carbon and hydrogen and and oxygen, and this N bond here is actually holding the oxygen molecules away from the fuel elements, and so they cannot react until this bond is cleaved, and the oxygen atoms can start to interact with the fuel atoms. Okay, but because there are oxidizer elements and fuel elements, this RDX molecule, if given an ignition stimulus, will burn by itself. Okay, and I'm not going to go through this whole thing, but other energetic materials that have nitro groups, there is nitromethane. So if you go to Gator Nationals, which is here in spring, that is just a methyl radical, or it's basically methane, and they cleaved off one of the hydrogen atoms and they replaced it with a nitro group. That's what nitromethane is. It's a liquid, basically TNT. That is essentially a benzene ring, and they cleaved off some of the hydrogen atoms and replaced it with a nitro group. HMX, that's similar to basically RDX, except for there is an extra nitrogen and extra carbon atom in that ring structure, but it's the same thing. CL20, CL stands for China Lake. That's a high density energetic material, and molecularly the most, probably one of the best energetic materials is octonitrocubane. It's the sort of lattice structure of carbon atoms with a bunch of nitro groups. Unfortunately, it's not practical. It's so expensive to make that it is worth more than gold by weight, and so, but it has been made. Okay, and EMs with nitrate groups, petin. Some of the terrorists use petin, and that's a Russian explosive. That's Petra. Yeah, again, I'm not going to even bother trying to pronounce these fancy chemical names here, but here is a molecule of petin, and notice here these things here. Those are the nitrate groups, ONO2. Here is nitroglycerin. Not used that much, basically because it's very shock sensitive. If you bump it too hard, it will, even in the lab, it will blow up on you. Nitric oxide, that's a very powerful oxidizer. It's used in some rocket and satellite applications. And it's given the moniker red fuming nitric acid if it is greater than 86% molality. It is extremely reactive stuff. And also there's ammonium nitrate, that's essentially fertilizer. If you mix that with a little bit of fuel, such as oil, you've made ANFO, which is an explosive, and it's a salt consisting of basically NH4 and basically NO3, which are arranged into a crystalline structure. Okay, and then I'll go over this last slide, and then we'll stop for the day. And then there are energetic materials with basically chlorates and azide groups. There's ammonium perchlorate, or AP. We will be discussing this one quite a bit in class. And these are also salts. So they form a solid crystalline structure with these basically with these cations and basically ions arranged in a crystalline arrangement. And there's also lead azide that was used as a that was used in the past. And while there is no oxidizer with this, this N3 group here is extremely energetic because remember you have all these double bonds here, and there's a lot of energy in those if you can get those to react and burn. And so, and there is a whole slew of these things, and I will not be discussing them all at this point, but I guess that's it for today, and we will carry on starting on Friday. Are there any questions? Okay.
None for me. Thank you.
Yep. Thanks, guys.
Thank you.
Have
Thank
a
you.
good day.
You too.
You too.